Okay, so the only one we don't have is number 9, so we'll do that in a minute. But let's go ahead and look at our results. Yep, so here are the multiple regression results, and I tried to make notes as we go through the output on as far as which assumption we're talking about. Okay, so this should match what you have there on page 2. Alright, so I made a note on page 2 that Durbin-Watson value, that's related to your assumption, number 7. And it is between 1 and 3, so we're fine there. Now we're going to kind of switch out of assumption world, and I'll just mention really briefly, we're going to come back to this and dig a little deeper with it, but this model summary table also has your overall information. So it's saying that your predictors combine to explain 18.4% of salary, that variability in salary. And I made a little note there. So you have your R, which remember is completely the same as Pearson R. We just call it multiple R because we're dealing with multiple predictors. And then R squared is exactly, thankfully, what it looks like on that table for once. Okay, so it's the square of R. And that's when we can start talking about percentages. So adjusted R squared is where SPSS goes in and replicates the study for you and gives you a prediction of what would your R squared change to under repeated samplings. So it does some bootstrap methods or some other internal replication methods. It doesn't actually go out and do the study again, but it will, from Andy's 200 and some odd participants, it will randomly sample from those 230 over and over and over and over again, maybe 500 times, run the multiple regression again, and again, and see how much does that R square fluctuate. So it's helping you with the sampling error you have going on. What is it about your sample that might be giving you your specific 18.4? Well, if we repeated it, SPSS again runs the simulation, it turns out that it would adjust downward just a little bit, and it usually does. So there's something that the initial R squared is a little bit inflated, but not too bad.
Do we need to include that bootstrap stuff?
Oh, no, that was just free information. Because you don't have enough, you're trying to cram in right now. But no, just the two pieces I noted there. So the R squared and the multiple R, or just the big R. So the 0.429 and then the R squared of 18. So age, years, and beauty combine to explain 18.4% of salary. And we interpret that effect size the same way you've been doing your partial A squared, you know, as far as what's large and what's small. And I think everybody has been commenting on, you know, if they came out with a minuscule effect size or what seemed pretty big, you know, you definitely put it back in the context of your research. So is 18.4 big? Well, I don't know, kind of, sort of, depends on what the salary model research out there says. Okay, so the next table is at the top of your page 3. This is just giving you an indication of whether or not your model is statistically significant. I don't usually interpret that at all because it's almost useless to me, because I've already found out this information right here, how good my predictors are. They're pretty good, 18.4%. So whether or not it's statistically significant, it's kind of, okay, great, it's significant. But that was just a little FYI there. Okay, so let's look at the coefficients. This is where I was talking about, now we can start to get an indication of who's getting the most credit, or which variable is getting the most credit for explaining that 18.4%. So we have to keep remembering, and you can interpret the unstandardized coefficients, we're looking at the B there, or you can interpret the standardized coefficients, beta, and it doesn't matter because they're gonna give you the same relative information. And so it is absolute value, and you're just simply looking for the one with the biggest absolute value. And you can declare that that one is the most important predictor of salary. So if we put them in order from biggest, so let's look at the B weights, the unstandardized. So which one has the largest absolute value there? Age. So we could say in our write-up that age is the best predictor of daily salary because it has the largest coefficient.
So we're kind of stepping away from the assumptions right now?
Mhm.
Okay.
So we're looking at the beta.
You can, or you can look at the beta or the B. Either one, they'll give you the same information. It's just one's standardized, one's not.
So earlier when we talked about possibly throwing one out, this would be one we would want to keep, is age, to discuss being the highest predictor of salary.
It could be, but the problem is if you threw out number of years as a model, it'll change these values. So you'd have to run it again and see what it changed to. But you might get a higher R squared value, and that's a good thing. And we could try that and see what happens. Number of years as a model kind of came in second place, and then attractiveness is in last place. So this rating of attractiveness is really not doing that great of a job of explaining or predicting the salary, daily salary. Now this is where, if you think about that equation of a line, this is where those values come from. So this is literally the multipliers that are being used. So you have a constant over here, and that is often B, plus age times either B or beta, whichever, you just have to be consistent. We'll just say beta, 0.942, plus years times -0.548, plus beauty times 0.152. All right, so that's kind of running together, but if you were wondering where these values came from, because remember, we can get SPSS to save these for us, but that's where it's coming from. So we take everybody's a person, so think about your rows in SPSS. Person 1, we have this intercept. That's where your line crosses the y-axis, whatever that is. It's just a standard value. Plus that person's age times this, plus that person's years in the business times that, plus their beauty score times this. And that's where this predicted score comes from. So that's really what's happening. And in all of the general linear model statistics, from this up through the most complicated, this type of math where you have these weights that are applied to variables is what's happening really in getting some sort of synthetic score. So here's our synthetic score, those predicted values. Then the predicted value is being correlated with the salary. And that's where we got that 0.84 or 18.4%. Okay. Now, if all of that made you go, oh crap, that's okay. Just kind of block that part out and remember that, look at this table to tell you who's getting the most credit for explaining. Because remember, we said we'd get sort of an overall answer, and for this, it was 18.4%. Then you can go in and pinpoint and say, you know what, age is getting the most credit for explaining that 18.4%, followed by years and then followed by beauty. Now this is an inverse relationship, which makes sense, right? The older they get, the less they're making per day. So that's what that negative value is indicating. Okay, but if you're wondering sort of how does it all work, that's the gist of it. Okay, and yeah, we are jumping back and forth between assumptions and then the results, because that's just kind of how they're coming across. But we'll run another one and just try to solidify some of this. Okay, but before we leave this and do some more talking, let's look at, here is where our VIF came out. So now if we jump back to that assumption 5, here's where it comes out. And we talked earlier about it being 12, which is greater than the 10 that we want. And so that is just saying, that's kind of a confirmation of what we were saying before, that we have a couple of variables that are probably too highly correlated. We should probably drop one of them. And the good news is you can drop one and run it, look at your result. Then put it back in, drop the other one, run it. You know, you can play with it to see how they each come out.
But it's okay if we just say, drop it.
Yep. So there's that. All right, so here is our histogram of residuals that we asked for. So that is on page 5 of your output. And I made a note there, that's assumption 8. So you as a researcher, you're eyeballing it and deciding, does that look normally distributed? Not bad, but pretty good. All right, then we'll scroll down and look at our scatter plot of our dependent variable, our z-resid and our z-pred. So that's your homoscedasticity, and we're looking for a funnel shape. Okay, do you see the funnel?
Yeah.
Don't drink before you do this. There's kind of a funnel thing going on here, so
You
again,
end
that's,
up with some homoscedasticity.
you're gonna be heteroscedastic. You can be whatever you want, we're all friends here. Alright, okay, so the last few pages are assumption 9. And remember, assumption 9 is, we're just checking, hey, are we modeling a linear relationship here or not? Okay, so let me show you how to get those. We're gonna go to our graphs and our chart builder. And you would not have to put all of these in your write-up. There's a lot of trust going on here, right? We have to trust if the researcher says the assumption of linearity was evaluated through looking at the scatter plot, blah, 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 and the assumption was met. You know, we have to trust them because usually, especially in a journal, they're not gonna give you room to put all these scatter plots. So there is some degree of trust here. But we need a scatter plot. So if we click on, have you guys looked at the chart builder very much? It's pretty neat. And it's pretty intuitive, it's not bad. But I know I need a scatter plot, and here it says scatter. I'm gonna take the simplest one and drag it up to the top. You don't need that. So it's an X and a Y axis. Okay, so if I look back at my directions there, it says the dependent variable in each predictor. All right, so what's my dependent variable? Salary. So I'm just gonna take it on the X and just leave it there. My first predictor I'll try is age. Okay, so I need to do this one first. And I told you guys about these dots, right? They're just an example. Don't trust the dots. Then you say okay. Now this is gonna match what's on your output here in your handout. So this is age and salary. What do you think? Is that a linear relationship? Can you, and remember linear, we're looking for a line that kind of captures some of the points. I don't know, what do you guys
Just
think?
a line, yeah.